Hello and welcome students. In this lecture of derivatives, we are going to work on the theorems of derivatives. Theorems on derivatives. Sometimes it is also known as theories on derivatives, or it is known as the algebra of derivatives. Now here what we are doing is we are going to prove certain theorems which we are using for solving problems, like if we have d by dx of sine x into log x. So what do? You use product rule. What do you write? You write sine x d by dx of log x plus log x d by dx of sine x. This is product. So this is based on a theorem which is known as derivative of product of two functions. It is d by dx of u into v. That is u d by dx of v plus v d by dx of u. And this we have already proved in 11th standard. We have proved certain theorems in 11th standard. And which were those theorems which we have proved in 11th standard? Those were, see, in 11th standard we have already done d by dx of u plus v is equal to d by dx of u plus d by dx of v. That is the derivative of sum of two functions. What do? We write derivative of individual functions and add. So this we have done. If we have a negative sign here, then what we write? We write negative. This also we have done. So 1 and 2, this is done. Then you have the third rule, d by dx of u into v. This is also done. And what was the fourth rule? D by dx of u upon v. We have division rule, d by dx of u upon v. What is this? What is it equal to? It is v d by dx of u minus u d by dx of v upon v square. Okay, this is also done where v square is not 0. We have done this. And the last one that we did last year, the fifth theorem that we did last year was d by dx of ku, k into u, where k is a constant. What is it equal to? It is k times d by dx of u. Sorry, we have already proved these theorems. If you want a revision of this, you'll have to watch that video. So what are we going to do in this lecture? We are going to prove some more theories, which are theory of composite function, which is chain rule, the theory of parametric function, theory of inverse functions, etc. Okay. See, the first theorem that I'm going to take here is, the first one is theorem on derivative of composite functions, or you can say, or theorem on chain rule. Now you all know what do we mean by chain rule. Suppose you have d by dx of sine of log x. How do you differentiate this? You write d by dx of sine log x. So the function is sine, but the variable is not x. You are differentiating with respect to x. So what is it? It is log x. So its derivative, what do you write the derivative as? You write cos of log x into d by dx of log x. This is the method that you apply for derivative of sine of log x with respect to it. This is chain rule. Cos log x into d by dx of log x. This is chain rule. So how is it going? It is going on a theorem. There is a rule for which, there is a rule that which we are using for this differentiating. Now suppose you had here, if you had d by dx of square root of sine of log x, then what would have been the derivative? See, then it will be one more step added to what you wrote. See, now this is which function? Square root function, but it is not square root of x. See, you are differentiating with respect to x, but this is not square root of x. What it is? It is root of f of x. So its derivative will be 1 upon 2 root sine log x into d by dx of sine log x. You see this? That is cos log x into d by dx of log x. That is 1 upon x. You see this into d by dx. So you check here what happened. Here you had sine log x. So its derivative was cos log x d by dx of log x. But when you have root of sine log, then it is this. Now just imagine, students, if you would write here, suppose you write d by dx of, sine inverse of square root of sine log x. Now what are you doing? You are adding one more branch to it. You see this? You are adding one more branch. So it will be 1 upon square root of 1 minus root of sine log x the whole square into d by dx of root sine log x, which will be 1 upon 2 root sine log x into d by dx of sine log x, which is cos log x, and then so on, so on. So the method you already know. What are we going to do? We are going to prove this theorem today. You already know how to differentiate. Now you are going to prove it. So I will write the theory here. Okay. See, what is the theorem? The statement of the theorem, which you will get in exam. In the question paper, you will see something like this. See, it will be if so here we have theorem on composite function. If y equals to f of u is a differentiable function of u. Very simple theory it is. Differentiable function of u and u equals to g of x. Let me change the color. And u equals to g of x is a differentiable function of x, is a differentiable function of x such that the composite function see y equals to f of u, right? F of u, and what is u? U is g of x. So now here you will replace u by g of x. So you will get the composite function, but that such that the composite function y equals to f of u, but don't write u anymore, right? G of x. They have already said u is g of x, such that the composite function f of g of x is a differentiable function of x. Then prove that d by dx of y is equal to d by d u of y into d by dx of u. dy by du into du by dx. See, this is what we have to prove. So first what I will do is, see, I will give you a technique by which you will remember this. Okay. First you have to learn the theorem. See, Now, how do I make you learn the theorem? Is just before you see, what am I given? I'm given here that y is a differentiable function of u and u is a differentiable function of x. So you have to remember like this. Whatever I am doing here, you have to remember this. Y is a differential function of u, u is a differentiable function of x. Now see students, when y is a differentiable function of u, what does that indicate? It simply indicates that I can differentiate y with respect to u. It means I will get derivative of, try to understand, I will get derivative of y with respect to u. It means I'll get here d by du of y. Try understanding. What will I get? I will get d by du of y. I can differentiate y with respect to u. I repeat, y with respect to u. Okay. What more am I given? I'm given that u is a differentiable function of x. Clearly said, you can check. If y equals to f of u is a differentiable function of u, y is a differential function of u. U equal to g of x is a differentiable function of x. Are you getting? So, and here what you have, u is a differentiable function of x. So when u is a differentiable function of x, okay, you can get derivative of u with respect to x. That is, you can get d by dx of u. But what am I interested in? I'm interested in d by dx of y. I want derivative of y with respect to x. That is, I'm interested in d by dx of y. I want d by dx of y. So the theorem says that this is equal to this into this. That is what it is. See, dy by dx is dy by du into du by dx. This is the theorem. Okay. Now, one more thing that I'd like to say here. You know, students, when they say y is a differentiable function of u, what do they actually mean? See, it's very simple. What is happening? Suppose you have sine of log x. Okay, you have y equals to sine of log x. So when you have y equals to sine of log x, you can treat this log x as u. This log x, you can take it as u. So if you take this log x as u, what will happen? Suppose you take this log x as u. You write let u equals to log of x. So the moment you write u as log x, what will happen to y? Y will become sine of u. You understand? So see, y is a differentiable function of u. Y is a differentiable function of u. You can check sine y is sine u, and u is differentiable function of x. U is differentiable function of x. See, this is y equals to, how simple it is. This is y equals to f of u. See, y is sine u. And what is this? This is u equals to g of x. U is log x. And what is this? This is y equals to f of g of x. F of g of x. Okay. So we just have to prove here. See, you have learned to differentiate directly. You have learned to differentiate directly. But here what is happening? You have to prove it, that how is the method. You have to prove that how you are differentiating, like the method which you are applying to differentiate y equals to sine of log x, that method is nothing but what you have written here. That method is nothing but what you have written here. The only thing is, we have proved it. We have been using that method without having done the theorem. That is the normal practice. We had been using that without having done the theorem. So I will now associate that method with this theorem. Get me a minute. See what it was. See what it was. It was y equals to sine log x. Y equals to sine of log x, right? Yes. Now see, if y equals to sine of log x, you take u as log x. You write u equals to log x. So what will y become? Y will become sine of u. Now since you have y as sine of u, you differentiate with respect to u. You differentiate this with respect to u. Now, when you differentiate this with respect to u, what do you get? You get d by du of y, which is d by du of sine u, d by du of sine u. That is cos of u. That is cos of u. Okay, you got d by du of y. Further, what is y here? Y is log x. Y is log. So if y equals to log x, let me I'm sorry, not y, it is u. I'm sorry. What is u here? U is log x. So if u is log x, you differentiate this with respect to x because it is a function of x. So what do you get? You get d by dx of u as d by dx of log x, d by dx of log x, which is equal to 1 upon x. Okay. So see, students, you got dy by du and you got du by dx. Just multiply these two. Okay, as I said, now multiply. Multiply this dy by du with du by dx. Multiply and check what you are getting. Okay, let us multiply and check what we are getting. So if I multiply, I will get here dy by du into du by dx equals to cos u into 1 by x. Cos u into 1 by x. And what is u? U is log x. So this is cos of log x. This is cos of log x. Cos of log x into 1 upon x. Cos of log x into 1 upon x. What is this? It is dy by du into du by dx. You can check. The product of this is cos log x into 1 upon x. And if I had differentiated this directly, what would I have got? If I had differentiated this directly, what would I have got? I would have got the same thing. See, if I differentiate this directly with respect to x, here what I did not differentiate directly. I applied the theorem. I repeat, here I'm applying the theorem. Why? See, I'm taking y as sine of u, differentiating with respect to u. I got dy by du. Then I'm taking u as log x, differentiating with respect to x, getting du by dx, and then multiplying dy by du by dx. Okay, I got something. What? Cos log x into 1 upon x. But if I had differentiated this directly, see, d by dx of y, what would be that? You know, it will be dy by dx. If you go directly, it will be cos log x into derivative of log x, which is 1 upon x. See, are you not getting same thing? Dy by dx is dy by du into du by dx, and that is what we have to prove here. Okay, so I will now, I hope you have understood this. See, I just want to tell you is we had been using the theorem to prove to find the derivative of composite functions. The thing is, we had been using it directly, okay, without having proved it. But today what we are going to do it, we are going to prove it. So let us start with the proof. Let us now start with the proof. First, you will write the statement. Now, students, this theorem, sometimes they ask for 3 marks, sometimes they might even ask for 4 marks. So you will not cut short the steps which I'm writing. Okay, you will try writing all the steps which I give here. So please listen to the learn the steps. See, the first step would be, as you know, that y is a differentiable function of u is a differentiable function of x. Now from this, what you understand, that x is the most basic variable. X is the most basic variable. That is, this is the basic variable. Okay, that is the first change that will occur, it will be in x. Okay, so you will start your statement as follows. It is very important that you have to recognize the basic variable. The basic variable is x. So the first change will occur in x. Because there is a change in x, there would be a change in u. First change in x, and then after that change in u, and then after change in u, there will be change in y. Okay. Now, when you have a change in x, why there is a change in u? Because they have clearly said that u is a function of x. So u depends on x. So because of the dependency, there will be a change in u. And since y depends on u, there will be change in u. So see, look at the first statement. I will write here. So my proof starts from here. See, I will write here. Let delta x be a small increment in x. Therefore, the corresponding increments in u and y are delta u and delta y respectively. I hope you understood this statement. Okay, what is the first statement? You wrote, let delta x be a small increment in x, the basic variable. Now, because there is a increment in x, there would be a increment in u and increment in y. There will be an increment in u and increment in y. Okay. What is increment in u? Increment in u is delta u and increment in y is delta y. Now look at the next step. The next step is very interesting. Here I will write let. Okay. Now since delta u is a small increment, remember I write here, since delta x is a very small increment, what does it mean? It means that therefore delta x tends to 0. Remember, delta x is very small. It is not equal to 0, it is tending to 0. That is delta x is not equal to 0. Remember, this small increment in x that you took, it is not equal to 0. It is only tending to 0. That delta x is tending to 0. Similarly, the other two small increments, okay, what? Delta u tends to 0 and delta y tends to 0. The other two increments are also very small. Obviously, if there is a small increment in x, there will be small increment in u and y, right? So here, what it is? That is, again you write that delta u not equal to 0 and delta y also not equal to 0. This is very important. Second step. What was the first step, students? The first step was the assumption. Second step is you writing that delta u, delta x, and delta y, they are non-zero. This is your second step. Now look at the third step. The third step is the deciding step of the theory. Okay, it will give the structure to your theorem. See, the third step is here. See, what you have to prove is here. What you have to prove is here on the screen. This you will see even in the question paper, they want you to prove this. So what is to be proved? Let me write here once again what they want us to prove. They want us to prove that dy by dx is equal to dy by du into du by dx. You know, students, what I will write? I write here, see, I'll write here, we can write, let me first write and then I'll explain. We can write delta y by delta x equals to delta y by delta u into delta u by delta x at any given time. At any given point in time, this is what I can always say. Yes, if you are saying, how can we say this? See, it is very simple. It is very simple. Tell me, if I have 5 upon 7 into 7 upon 8, can I not write this as 5 upon 8? Yeah, definitely. See, this 7 cancels. Same way here, delta u cancels. What you have? You have delta y by delta x. You have delta y by delta x. So that is what I'm doing. What I'm writing? I'm writing delta y by delta x as delta y by delta u into delta u by delta x. Now, if you have some doubt here that what if I forget this step, what if I don't remember what I should write here? See, very simple. Whatever they are asking you to prove, in that you replace d by delta. You replace these d by delta, and when you replace d by delta, you will get the same. You see here, delta y by delta x, delta y by delta u into delta u by delta x. Okay, this is what I have done. Remember, these are all small increments. What are they? They are all small increments. And remember, students, the reason that we proved, the reason for I writing that they all are not zero is this only, that we had to write them in the denominator. See, I wrote that they are not zero. Why? Because here I have delta x and delta u in denominator. This equation, I will write it as 1. This is my first equation, that is equation number 1. Now see the next step, what I do. The next step is also very interesting. How simple this theorem is. And let me assure you, if you learn one, you can solve the rest. So this is my third step so far. So first step, second step, and this is my third step. So far, this is my third step. Okay. Now I go for the fourth step. See, the fourth step I write here is taking limit on both sides as delta x tending to 0. Remember, students, if you have a question, why take limit as when delta x tends to 0? Why not when delta u tends to 0? Why not when delta y tends to 0? It is because delta x is the basic variable. See, you started with your basic variable, so you will write delta x tends to 0. Got that? So here I write here, taking limit on both sides as delta x tending to 0. Taking limit on both sides as delta x tending to 0. So see here what I get. I will get here, therefore, limit delta x tending to 0, delta y by delta x. Okay. And this side I have limit delta x tending to 0, delta y by delta u into delta u by delta x. Okay, see, limit on the right, limit on the left. Now, see, In the next step, I will now write separate limits. I will write the separate limits. So here I have limit delta x tending to 0, delta y by delta u into limit delta x tending to 0, delta u by delta x. See this? And this side what I have limit delta x tending to 0, delta y by delta y by delta x. Okay. Now see the next step. Students, this one I write it as 2, equation number 2. Now in this, something that I noticed, I would like to bring to your notice. Let's see here, delta y by delta u. See, the denominator is delta u. And here the denominator is delta x. Now see, wherever you have denominator as delta x, where you have denominator as delta x, it is okay. Okay. But where you have denominator as delta u, it is not okay. You will have to bring delta x here. Why do I have to bring delta x here? Because by the definition of derivative, we have done it that by the definition of derivative, we have done that if you have delta u by delta x and delta x tending to 0, then this will be du by dx. Then this is du by dx. Okay, this is by the definition of derivative, which we have done when we started with the derivative. See here, if I have delta u upon delta x, and I'm given that delta x tends to 0, then this will become what? This will become du by dx. If I have delta x upon delta p, and I'm given delta p tending to 0, then this will get me derivative of x with respect to p, that is dx by dp. What is important? By definition of derivative, whatever change that you have in the denominator, it is that change which should tend to 0. Then the limiting value of this is the derivative of numerator variable with respect to denominator variable. So keeping this in mind, which is the definition of derivative, what I will do here is, see, I will write here I have delta u. I don't want delta u. I want delta x. Okay, either you will have to change this to delta x, or you will have to change this to delta u. Okay, so what I do here is, see, now it is not possible for us to change this to delta x. That is not possible. You can't change the denominator. What we will do, we will write here, see, whatever your denominator is, whatever you have in the denominator, that should tend to 0. So like here it is all okay. Where we have delta x, it is all okay. Where we have delta x, it is all okay. Why? Because denominator is delta x, and here you have delta x tending to 0, but here it is not okay. Denominator is delta u. We should have here delta u tending to 0. So what do I do? See, I'll write here. As delta x tending to 0, we can write delta u tending to 0. Why so? Because it is given, because u is a differentiable function of x. It is given u is a differentiable function of x. So definitely u depends on x. So there is a small change. When the change in x is approaching 0, the change in u will also approach 0. Now using this, equation 2 will become, see what equation 2 will become. Therefore, equation 2 can be written as, how you can write it? It can be written as limit delta x tending to 0, delta y by delta x equals to, see here, denominator is delta u, so I will write here delta u equals to limit delta u tending to 0, delta y by delta u into this side. It was, the second factor was all okay, limit delta x tending to 0, delta u by delta x, and this is equation number 3. Okay, now what I will do is, so what I did here, since I had delta u, I wanted delta u here, so I did this part, and this is my step number. This is my step number 5. Okay, this was step number 4, taking limit, step number 4, and then changing delta x tending to 0 to delta u is step number 5. This is my step number 5. Now we are proceeding towards the last final step, that is applying the definition. See, I'll write here, by definition, see, this one, I write here, limit delta x tending to 0, delta u by delta x is du by dx, okay, when the limit exists and limit is finite, when we have the finite, and when the limit exists and it is finite, okay, exist and finite. Then here, okay, when the limit exists and limit is finite, the second one, we are working on the RHS side. I'll write here limit delta u tending to 0, delta y upon delta u. What is this equal to? It is dy by du. And here also I will write exist and finite, right? Now see, on the left hand side, what I notice that on the left hand side, all the limits exist and they are finite. Okay, because see, we have already been given that u is a differentiable function of x, so definitely the definition will work here. Okay, and for this also the definition will work because we have been given that y is a differentiable function of u. So definitely the limits would exist and be finite. Now I will write, since all the limits on the left hand side exist and they are finite, so the limit on the right hand side will also exist and it will be finite. If all the limits on the right hand side, I'm sorry if I said it otherwise. Okay, I repeat it again. See, if all the limits on the right hand side of this equation 3, they exist and they are finite, so definitely, since we have equal to sign, the limit on the left hand side will also exist and it will be finite. So I'll write here, since all the limits on RHS exist and are finite, therefore the limit on LHS will also exist and it will be finite. Okay, so what you can write, therefore this will become, therefore limit delta x tending to 0, delta y by delta x will be dy by dx. Okay, so using, now see here, I can write this as So this is 4. I can write this as 4. See, I can write this as 4. I'm sorry. I can write this as 4, this one as 5, and this one as 6. So using 4, 5, 6, and 3, therefore, we get what you will get using 4, 5, 6, and 3. You will get dy by dx. See, this was dy by dx equals to dy by du into du by dx equals to dy by du into du by dx. Hence, proved. I'm sorry. Hence, proved. See, this is what you have to do. This is step. This is last step. This is last step, which I will call as step number 6. So that is applying the definition. This is step number 6. So there is a set pattern, student. What is the first step? Let me repeat. What was the first step? The first step was to realize the basic variable, which was delta x. So let delta, you assume a small increment delta x in x. For that, the corresponding increment in u and y are delta u, delta y. Then what? Then you have to write that none of them are 0. None of them are 0. They all are close. They are all approaching 0, very close to 0. And then what you do, then whatever they want you to prove, replace all d by delta, you write this equation. Then you take limit on both sides as the basic variable tend to 0. Then separate the limit and then look at the denominator. In denominator, whatever variable you have, it is that variable which should tend to 0. So if elsewhere it was all okay, only this one was not okay. So I made it here delta x. Okay. The next I have is I changed the equation. Since it was delta u, I brought delta u here, and after that I use a definition, and that is all. I hope you followed it. Please copy this very simple theorem. Now, having proved the theorem on composite function or chain rule, we have another theorem to be proved, that is theorem on parametric function. Now see, believe me students that this you are going to prove it without any stress because you have already understood the theorem on composite function or chain rule. Now see here, what is it? Let us read the statement first. The statement says, if x equals to f of t and y equals to g of t, both are differentiable functions of t. Okay, so that is you can differentiate x with respect to t. You can differentiate x with respect to t. What does it mean? It means you can obtain d by dt of x. Yeah, because x equals to f of t is a differentiable function of t, so you can obtain d by dt of x. Very good. Y equals to g of t is also differentiable function of t. What does it mean? You can differentiate y with respect to t. That is, you can obtain d by dt of y. But you know what we are interested in? See, x is equal to f of t. X is a function of t. Y is a function of t. Okay, so I can differentiate x with respect to t, y with respect to t, but I'm interested in derivative of y with respect to x. X is a function of t. Y is also a function of t. Both are functions of t. I can get dx by dt. I can get dy by dt, but what I want dy by dx. So the theorem says that dy by dx will be dy by dt upon dx by dt. That's it. Okay, but now we have to prove it. See, how do I prove? For proving, very simple. For proving, I will start with my basic variable. Now, students, you have how many variables you see here? Like in the previous theorem, you had y as a function of u as a function of x. So you had 3 variables, of which this was the basic variable because the changes would occur in this first, then this, then this. Okay? Yes. If you see here, how many variables do you see in the statement? See, you have x, t, and y. You have x, you have y, and you have t. what do you think is the basic variable? It is needless to be said, my dear students, that t is the basic variable. Why? Because x is a function of t. It is clearly said x is a function of t. So definitely there will be a change in t, then only the change in x. And y is also a function of t. So there is a change in t, then only there will be a change in y. So the basic variable here is t. And once I know the basic variable, you know what is my next step. My next step is, see, my proof will start. And how will I start my proof? You know, I will write here, the first step is let delta t be a small increment, in t. This is, and then the corresponding increments in the other variables. Therefore, the corresponding increments in x and y are delta x and delta y respectively. This is my second step. This is my first step. Okay, the changes. Now I go for the second step. What is second step? I will have to write that none of these change is equal to 0. That is what is my second step. So I will write here, since delta t tends to 0. Okay, this implies what? This implies that is delta t is not equal to 0. So is the case with the other. Okay, also delta x tends to 0 and delta y tends to 0. They all are small changes. That is, delta x is not 0 and delta y is also not equal to 0. This you have to write. This is the end of the second step. Now we go to the third step. You remember what the third step was? Yes. The third step was we would write exactly what we have to prove here. Okay, as an equation, replacing all d by delta. So see, what do I write here? I will write here, we can write, see, delta y by delta x is equal to delta y by delta t upon delta x by delta t. This is what I will write. Okay. Yes, I can do it. Why? Because delta t, delta x, they are not 0. So I can always have them in denominator. I can do this. What is next step? This is my equation number 1. Okay. This is, see, basically, you know, what you are writing here, these delta y, delta t, delta x, they all are small numbers. So as such, you know, if I have 5 upon 7 upon 3 upon 7, wouldn't this be equal to 5 by 3? Definitely yes. So we are following exactly the same concept here. But in order to help you out, I'm telling you that how would you remember this step? You just remember that whatever you have here, which you have to prove, you replace all d by delta and you will get this step. Okay. Next step is, you know, the next step is I will write taking limit on both sides of equation 1 as delta t tends to 0. Remember, the limit you will apply, you will take the limit as the basic variable changes to the basic variable change tending to 0. You will take the limits as the change in the basic variable tends to 0. Okay, the basic variable here is t. So you will apply the limits when delta t tends to 0, and that you will do on both sides. So next step you have limit delta t tends to 0, delta y by delta x And here also you will have limit. You will have here limit delta t tends to 0, delta y by delta t, and limit delta t tends to 0, delta x by delta t. Okay. Now what I will do is, see, I will take this. The next step is, okay, next step is, see, the denominator here is delta t, and what is tending to 0, delta t. So this is all okay. Here also denominator is delta t. See, this is delta t, and delta t tends to 0. So this is okay. But see, this side it is not okay. Here you have denominator delta x. It should be delta x tending to 0. So what I will do, I will write, I will try to make this delta x, I'm sorry, I will try to make this delta t as delta x. And for this, I have a very simple explanation. I will write as, I will write here as delta t tends to 0, we can write as delta t tends to 0, delta x tends to 0. Why? Simply because x is a differentiable function of t, because x is a differentiable function of t. So definitely when the change in t will diminish, it will approach 0, the change in x would also approach 0. Now using this equation, this is equation number 2. Using this, equation 2 becomes, I write here, using this equation 2 becomes, what does it become? See, it will become limit. On the left hand side, it will be, see, this was delta t, which will now be written as delta x, delta x. So it will become limit delta x tending to 0, delta y by delta x, and here you have limit, limit delta t tends to 0, delta y by delta t upon limit delta t tends to 0, delta x by delta t. Okay, see how simple. This is equation number 3. I'll repeat. See, what was the first step, my dear student? The first step was you assume the changes, right? What is the second step? You write that no change is 0. They are all tending to 0. What is the third step? Third step is you write this equation replacing d by delta and you take limit on both sides, right? What is the fourth step? The fourth step is you change as per the required denominator, right? Like here it was delta x, so we brought in delta x here. This is fourth step. And now the final step. What is the final step? The final step is, by definition, we will write the definition of derivatives and change every this delta form into d form. Okay, so this will become dy by dt, dx by dt, and dy by dx, and that's all. It is all done. It is all over. Okay, so here now we will start with the definition. See, the next step I write by definition. I write here by definition. See, this thing, limit delta t tends to 0, delta y by delta t is equal to dy by dt. And what I'll write here exist and finite. Okay. The next one, in the denominator, you will always write for the right hand side first. Remember, okay, always write for the right hand side first. So I will write here limit delta t tends to 0 and delta x upon delta t. By definition, it is dx by dt. And what would you write? You will write exist and finite. Now, having written this, now in the next step, what I'm writing here is very essential. It is very essential, and you will try writing it as it is. Please, my dear students, I'm writing the best possible shortest answer. Please do not cut short anything in this. Okay, I will write here as as the limit on RHS of equation 3 exists and are finite therefore the limit on LHS will also exist and will be finite. So what will happen? Therefore, this thing you can write, see here, what you will write, check what you have there. You have limit delta x tending to 0. Try to understand, students. You have limit delta x tending to 0, delta y by delta x. So see, when you have delta y by delta x and delta x tending to 0, so this will be dy by dx. Are you getting? It will be dy by dx. See, here you had delta y by delta t and delta t tends to 0. So this was dy by dt. This was dx by dt. This will be dy by dx. Okay, similar thing happened in the last one. See, this delta y by delta x and delta x tends to 0. This is dy by dx. When you have delta u by delta x, you wrote du by dx. When you had delta y by delta u and delta u tends to 0, you wrote dy by dt. That is very important. I hope you are following. See, delta u, delta x, so du by dx. And whatever you have here, you should have that number tending to 0. That change, that respective change should be very small. It should be approaching 0. So the next step I write here. See, now I write using, this is my 4, this is 5, this is 5 and 6. I write using 4, 5 and 6 in 3. What we get? Therefore, we get what you will get. You will get on the left hand side, dy by dx equals to dy by dt upon dx by dt. Okay, where dx by dt is not equal to 0. Where dx by dt is not equal to 0, hence true. Along with such theorem, you can get one question for 1 mark. So total it will be for 4 marks. And if it is only the theorem, then it will be for 3 marks. You can copy this now. I hope you followed it.